So, cryptography. I'm pretty sure most of you have already dealt with it some, but yeah, so I don't really know. I'll skip like the really boring stuff. Like cryptography is a thing that encrypts and decrypts data and makes it secure.
It's supposed to make it secure, doesn't it?
Yeah, supposed to. We're supposed to pass class. Doesn't mean everyone does.
It's like if you're not using salt, you're probably not doing it.
Yeah, y'all know that there's two types of ciphers when it comes to cryptography. Can't really spell. Asymmetric and symmetric. Rick. Yeah. And basically all it means is asymmetric requires a key for one key for encrypting and one key for decrypting, and then symmetric uses the same key. You might hear them called public key and private key for asymmetric. So public key would be the one that you have, or no, have it backwards. Yeah, public key is the one used for decrypting. Private key is the one used for encrypting. Also, since I'm not the leading expert or an expert at all in cryptography, if I say something wrong or you think of something to add, feel free to interrupt.
So you could potentially have one public key for several different pieces of data, but you have different private keys with asymmetric cryptography.
Yeah, and even for symmetric, you don't just have one key period. It's one key for each pair of users or something. So you could have, all these connections here and stuff, make a graph. That way you can do Dijkstra's algorithm. No, all right. So yeah, you'd have two keys and stuff or something for each of those. Yeah. And obviously, like, if you felt like writing it down, I guess you could say, like, complexity on that is linear, but that doesn't really matter. Yes, complexity analysis doesn't matter. N cubed is fine. Or n to the n. Yeah, so then, other than this is just very abstract. There's two types of ciphers. There's stream, which you can't really read there, and there's block. So stream ciphers are the simplest. That's like Caesar cipher, where you're literally translating one letter to another. So if you have like the key, 2, then that means A becomes C, just 2 letters over, and Z would become B. It will rotate around, and so on. So that's like an example of a stream cipher. So you might you just do something to each individual letter or character. It's not based off of anything else. It's independent. And the good thing about that is it's really fast. The bad thing is they're not as secure because they still have all the information there. It's like, like if you take Caesar cipher, for example, one, it's easy to break because there's 26 letters in the alphabet, and then it's also really insecure because all the change of the letters and stuff is all the same. It's all just relative. Block ciphers, on the other hand, are a little different. So basically with a block cipher, if you've got all this plain text that you want to encrypt, it takes it by a block at a time encrypts that, so that's in, encrypted stuff, and then it uses that to encrypt the next block and keeps doing that, so on and so forth. So each block relies on the one before it. And it's an example of that would be like the transposition cipher, which is when you have you have your plain text and you basically store it in a grid, and then you output it by the columns. I think if I remember right, that's how you do it. So yeah, it'll kind of jumble that up, and then the key basically determines the dimensions of the grid. So that would be like a block cipher. Yeah. On the actual encryption though, I haven't played around too much with many of them, mainly AES. And so that's advanced. Is it advanced? Yeah, advanced encryption standard, which is used I think it's used even by the government for classified information. So AES is pretty secure. It's also obviously a block cipher. Yeah, and the good thing about block cipher is it's really secure, or it's more secure than stream ciphers at least. The bad thing is it's usually a lot slower to actually encrypt and decrypt. Yeah. Then a single bit change in your plain text or your key and stuff will, pretty much always change your output, or whatever you want to call it, ciphertext. But the thing about block ciphers is there's different modes. Yeah, so you can find a list of modes. I think there's 14 accepted ones right now, and that's just the way that they're encrypted, or the way the blocks are used. Yeah, the only one, this looks like the simplest one probably. Yeah, this is kind of cool. So using that mode on an image, they have you can still see it. But the only one that I've really played around with is the cipher blockchaining, and they've got a pretty good picture here of what happens. So you have a IV, which you'll hear sometimes called a salt, which I don't really know why, but basically just stands for initialization vector, and it's used in it's used in the ciphers to alter it. So with this mode, they use it before actually doing the encryption each time. So it looks like they XOR it with plain text, run the encryption, and then the output of that block gets used as the IV for the next block, and so on and so forth. So that's for the encryption part. For the decryption part, it's just the opposite of that. You do it after the decryption each time. So that's pretty cool. And there's a bunch of these on here. So this is a propagating version of it, and they've got different attributes here too, whether you can make it you can paralyze it paralyze it where it can't move. No, I'm just kidding.
So you've heard of the Enigma machine, right?
Yeah.
Would you consider that to be a block cipher, since it encrypts each character as they're being typed?
I guess so. I mean, I'm not 100% sure how the Enigma machine worked, but
so put basically, it functioned a lot like a typewriter, but inside there were 3 different dials of different sizes, and what would happen is there would be a certain input, a certain set of numbers that each of the dials were set to. And as you type, one dial rotates. And when it's a full rotation, the next dial rotates.
And that changes it.
And each of the dial's positions determines which characters get mapped to other characters.
Yeah, that would be a block. That would be a block then.
Block though, because
I mean, if the dial changes each time, though, that's gonna affect your next one. Is the thing. If the dials change each time with each key press, then it would affect all the others. So it doesn't change according.
It doesn't matter. It does matter what key.
Do they? I don't know. If they change depending on the key press, then it is. Otherwise, I don't guess it would technically be considered one.
No, I don't believe it changes on what key is pressed. Just it starts at a certain value.
And just does it like constantly turn or?
No, each dial, like if we have a dial of 10, 12, 20, the first one would rotate 10 times for one tick.
Yeah.
Or a full rotation.
It changed like every hour, didn't it?
No, it changed every day.
Every day?
There was a list of different random
Yeah.
inputs.
Yeah.
And the way they broke.
Yeah, they made a movie on that actually. Had
It's really nice.
what's his name in it?
Cumberbatch.
Yeah. Corey would have known.
But the way they broke it was that there was a common pattern in the beginning of all of their intercepted messages, which was starting with what the weather was.
Yeah. So, yeah, as far as just this mode, like as an abstract block cipher mode, this would be pretty easy to implement just by itself.
Okay, I actually looked up the description of the invention. But basically, you have the rotors, like you were saying, and you would place the rotors in a certain position in order to get the proper encryption of the day. And there was actually like little reflectors on each of the rotors, and depending on what you typed on what reflected, if it reflected in the first rotor, second, or third, and when you typed the initial, it would like light up what the encrypted letter was. Yeah.
Wait, if I remember right, based on the position of the rotors, certain keys would turn certain dials, not just one for the next.
The dials would not physically turn until you physically turn them.
Right.
Like you turn them in order to get what the encryption, say for instance you have the first dial on 27, second dial on 72, and so on and so forth. Then all of the encryption machines would be on that those specific numbers for that day, and it would change every day.
Yes, that's right.
Yeah.
Anyway, so that's actually about all you really need to know for block ciphers and the modes they have. So AES is a block cipher, and I guess I should have pulled it up. Yeah, I figured that would happen. Yeah, so like I don't know what the top ciphers are, like the top 3. I would say this one's pretty high up there though. PGP is another good one, which is cool. That's pretty good privacy. Yeah. Like some people say that this is like the best and that's unbreakable, but I don't know. I'm a skeptic. But yeah, invented by Phil Zimmerman. I wish I had actually used this in the past. Well, other than like just command line tools. But yeah, I'm not sure how PGP works. Random key. But yeah, that's another good one. I think Zimmerman actually went to jail for a little while because he wouldn't like he wouldn't like help, I don't know, like the FBI or somebody like he wouldn't give them the information about his the cipher or like how to break it or something like that. So
Kind of like the backdoor on iPhone.
yeah, I don't know what happened in that ordeal, but with AES though, after I erase all this mess, you don't really have to know how any of it works on a low level unless you just want to. And I don't really know much about how it works other than like what you can read here. So yeah, like it's basically just pretty much all encryption is just linear algebra really. So if you're ever interested in trying to make your own cipher, it would help to have some linear algebra knowledge. But yeah, so it always operates on matrix 4x4. Yeah, the key sizes, it's like you have to have a specific length key to use AES. So I think the acceptable ones it probably says somewhere, but it's like, yeah, 128, 192, and 256. I thought there was another one, I guess not. Yeah. So, and then there's block size too. So, for Python, there's a library I've used before multiple times called PiCrypto. You just call it crypto when you're importing it, but it's got AES, it's got a bunch of others, and I wrote this class a while back to make it easy to encrypt and decrypt. So basically what you do is when you've got plain text here, it might not be in the right size or like an acceptable length to actually encrypt with AES. So you need to get the length of it and then pad it with something else so that it is the right length. So that's why I have this pad function here, and then the actual thing that I add on here is whatever, like, I mean, there are different ways you can do it. You could just use it like whatever character you wanted to and just put however many you needed onto the end. I think that might be bad practice though. Like, the way I've always seen to do is take the like amount of space that you need and then take that number and turn it into a character and then use that character. Yeah, because you can do that, and then when you're decrypting it, so you've got this bunch of mess here on the end. Yeah, you can use that to tell how much. Well, you decrypt it first of all, afterwards, and you'll get this same thing. And you can still tell how much is padding on the end and how much is your actual message. Doing it that way. Yeah, like I said, I guess it's really just whatever you want to do. But yeah, so like when you create this object, you just give it a key. I used a 256 SHA hash, so it just gets a hash of that key. And then this is the block size. I was using 32. All that you can change. And unpad, that just takes the padding off afterwards. And then got decrypt and encrypt. So like I said, the PiCrypto library that I use made it pretty easy. So this takes whatever message you want to encrypt, pads it to begin with, and then I create the initialization vector. And if you read like on where is it? No. Oh, I don't even know how I got to that page. I looked up Caesar cipher. There. Yeah, if you look somewhere for the initialization vector, they'll say it should be random, or at least pseudo-random. So the cipher or PiCrypto library here has a random thing built in that's supposedly better than random that comes with Python. Yeah, so you just use new with that, and then read in the block size, and that also affects it. And the cipher object, you just pass in all the stuff, and it's actually kind of funny that I've called this class AES cipher. I have a cipher within a cipher. I never thought about that. Yeah, so then you can pass in the mode here. So actually I should be able to change that if I wanted to in the future. Like everything else should stay the same, I believe. And then there's a base64 library in Python for doing encoding and decoding with that. So then decrypt is just the exact opposite. It's pretty easy. I have two basic examples though, neither of which actually use that class, but I'll upload this later if y'all ever want to use it. So this one, all I'm using is AES and nothing really fancy. So it creates a new AES cipher, and this is the key. And if you actually count the layers, that's 4, or I guess it could just, yeah, 17 selected, but it's 1, 2, 3, 4, 5, 6, 7, 8, 16. Oh, it says 17. Oh, I have the quote selected. Yeah, so this is 16 characters in length, so it works. It's not going to yell at me for that. And then this one is also 16 characters. Yeah, so the IV also is fine. And then the message to encrypt, and then all you have to do is use the cipher object, call encrypt, pass in the message. Then technically I could have just reused this up here for doing the decryption, but this is kind of showing, which I really don't know why I didn't. It doesn't make much sense because these lines are the same. But normally you wouldn't do both of them the same object or the same file. So, so yeah, if I run that, so yeah, it prints out the encrypted mess, which is bytes, and then the decrypted plain text. The little B thing is just Python's way of saying it's a Python bytes object. So anyway, then the other example I've got is a little bit better. So actually I am using that class, but for whatever reason I didn't import it. I don't know, I wrote this a little while back, but so what this is going to do is I've got my main function that takes these arguments, and then I can like just pass in command line arguments if I want to. Otherwise it'll ask for all of the necessary arguments. But so what it does is creates the cipher with the class that I wrote based off the key, and then got some other variables. Opens the file for reading in, and since we're dealing with bytes, you have to tell it to read as bytes, or read as binary, not your regular read. So stores that, and then mode, I just used 1 for encryption, 0 for decryption. So so yeah, that'll store either the ciphertext or the decrypted text. Then all it does is write it in that file. Pretty straightforward, and then all that's just ugly command line arguments. So yeah, I guess I probably should have showed this. So I've got a text file, my super secret text file. Oh yeah, wouldn't want anyone getting their hands on that.
He says is recording the meeting.
Oh no! It's alright, I'll encrypt the video and then upload it.
It's just gonna be random noise.
Yeah.
Like pseudo-random.
Have the description if you can crack this. Yes, so secret.text output. I don't know, output. And then I want to encrypt. So one, enter a key. Kyle is the man. There you go. So now if you look at that, it's a bunch of mess with UTF-8 encoded. Yeah. And then if you want to get it back, run it, output, that's our input file this time, and then yes, you want to decrypt it, and then Kyle is the man.
So if you use the wrong key to decode it, then it's
Yeah.
gonna look like even more garbage.
So now I'm gonna do it again, but with the wrong key. Try to use tab completion on. Alright, decrypt. Adam is the man. Nothing. Well, that's the thing with the block cipher, I guess, it is what causes it, but a lot of times if you do use the wrong key, you end up with just nothing. I guess it like destroys like a lot of data with that. So, yeah.
Cryptographical equivalent of an awkward silence.
Yeah. So those are those. I don't even remember. Yeah, so instead of just using command line like piping and stuff to basically encrypt a bunch of files and compress it, or whatever, I had this brilliant idea to do this. So basically, this is a thing I made. If you've got all these files here, it encrypts them all into one file of just ciphertext, and then I can run the program on this file. Well, first of all, I can specify if I want to delete these as well, and it will after the encryption, so I'm left with just that. And then you can run it on this file, and it creates all the files back as they were before. So I thought it was really cool, and then I was like, wait a second, I could just encrypt all these and then put that in like a tar file with like one line of bash. Anyway, you know, I learned how to do like crawling through like your file hierarchy though with this, because I made it so it works on folders and stuff recursively too, so you can do that. But I'm really glad I was using Git and version control with this though, because the first time I actually got it to work, I also accidentally encrypted and deleted this file. So I was like, yeah, I'm gonna undo that.
You encrypted and deleted the program.
The thing that allowed me to do it, yeah. Yeah, it's pretty bad. Anyway, so that's encryption, I guess. Yeah, PiCrypto is good. There's a few of them for Python. There's one just called Cryptography. Yeah, I don't think it's as good. I haven't used it much, but PiCrypto is a lot older and kind of seemed to be a little more stable. or at least years ago when I first found PiCrypto. As for other languages, I'm sure there's stuff out there. But yeah, and then so yeah, we've got like 25 minutes left. There's this problem that's totally about cryptography. I don't even know what PRNG stands for. Pseudo-random number generator. Yeah, well, yeah, that was hard to guess. Yeah, so this is a problem. They give you a number telling you how many test cases there are, and then for each test case they give you 2 epoch timestamps. This is like the start and this is the finish, so you have a range, and that range can be up to 1 million apart. I guess that's, what's that, it's in microseconds. Yeah, so it's not that bad really. But then after that they give you 10 numbers. These are numbers generated by calling next int with the range of 1,000. So you're going to get a number between 0 and 1,000 each time. So yeah, they do that and give you the first 10 numbers, and you have to figure out what seed they use to generate what number they use to seed the random number generator. So really it's pretty straightforward. You're just, the brute force, which is what I did, you can just loop through this range trying each of the each of these timestamps to seed the number generator, and then if you get the same first 10 numbers, then you know that's the right one, so you give them their output, which is the number used to seed and the next 10 numbers. So
I suppose the real issue is the number of calculations you do if that space was 1 million.
I mean, I think like if you look into the discussion, people apparently said that test case 4, the input was greater than 1 million actually. They're like, hey, the constraints are wrong. And then other people were like, yeah, but it doesn't really matter, it still runs. So
Program in Java 8.
Program in Java 3. How's that? I don't guess I have to do that, do I?
No.
What is Java?
Hail style.
Hey Adam, you should talk about the JVM sometime. I don't either. It's a virtual machine. The Java virtual machine. We could write Java bytecode. Yeah.
Java interpreter in Java.
Yeah. I've written a Python interpreter in Python.
I'm looking at a Python interpreter written in Python right now.
Yeah, it's pretty funny. Kyle, you remember the my import thing? You can import anything you want.
Oh yeah.
Yeah, I made a program once that is basically a wrapper for a Python interpreter, where any regular Python just runs, but when you do an import statement, if it imports successfully, then it's fine, it does it. But if you try to import anything else, it creates a Python file with that name and then puts a random like print statement in it or something, like with just a dictionary of messages that I had. So you could put like jokes in there or something if you wanted to. So you could do you can literally just say like import, I don't know, computer or garbage or something, and it would create that. So I thought it was clever.
Did I ever tell you about green text?
I don't think so.
It's an interpreted language. It's like wall code, but it's Python. If Python were like 4chan.
A built-in what interpreter?
JavaScript.
Ugh. But why would you want to use JavaScript? Yeah. Wait, you mean Java and JavaScript are two different things? What? So loop through a number of test cases. For each test case, we'll read in the timestamps. Stamp 1. And then the numbers. So they give you the first 10. Oh yeah, I use T up here so that I could use I later on, because I really don't care about T.
But I thought you loved T.
So we'll read in each number, which takes forever to read in things in Java. Cough, cough. I was like, well, why aren't you doing it in Python?
Let's say scanner is scan has like really weird overhead.
So we read in everything, and then
Scan has a lot of overhead. Not for reading into encryption.
oh no. So yeah, you want to loop through the range from the stamp. So and then make the random. Yeah. So we've got the random number generator. And then yeah, I was having the documentation pulled up. So they've got set seed somewhere. Yeah, there it is. So set seed R, I guess I should change that to long. And then yeah, like you said, this is the brute force way of doing it, so it's probably a better way of doing it. So yeah, I'll compare the first 10 numbers that I get from this to the numbers that I read in. Say not equal. Yeah. So then if we read into numbers and didn't fail, then should I move that? We'll read in 10 more, I guess, and yeah.
Wait, if you have it say Boolean failed code. Okay, yeah, you just don't stuff. Never mind.
Yeah. So system.out.print. Well. So we have to print the number they use, so that's going to be I. That was the seed, and then space. Then we've got to print out each number, each next thing, and a space. Then new line. And break. Yeah. So that's our massive for loop thing, which I think is it. Yeah. I should try this in Python, I guess. I don't know. I don't know if it has. I'd have to look up how to do the numbers. Woo! First try. I didn't get it on my first try earlier though. but that was only I did, but I didn't because I had syntax errors. I capitalized the I and N, and then there was something else where I used the N instead of a long. But after I fixed that, it passed. So it was basically first try. Yeah, I don't know. Python's
First try, third attempt.
3. I don't know if you can do. I guess you could do that. Yeah, I don't. I think I'm gonna try that. If I could actually type Python. Oh goodness. I guess I should do random.c. Okay. Oh. Wait. What'd they call it? Random range?
Rand range.
Ah, really? .509. Nah, they're not the same. I guess you do. I don't know.
Well, you do rand in with me.
Yeah, that's what I was thinking. But we're going for 877. Yeah, I guess you couldn't. I was looking at the discussion earlier, and somebody said, it was like, yeah, most of the solutions I've seen were in Java. It was like there were a few in Python and stuff. So.
That's what I was getting at when we started was, how do you, in a language that isn't Java, how do you determine the algorithm that actually just generates the random number for Java?
I mean, there's a... I don't know how that function is defined or what. I have no clue. By humans.
See, honestly, if I were to do random numbers, I'd probably just look for data sets on, radioactive decay or something like that. Brownian movement. Stuff that is truly random. Or as close as we could possibly get.
Yeah. Well, I think this problem was designed by Java or for Java. I mean, because they're talking about they mention it specifically there,
Right.
and then the code that they kind of use there is obviously Java.
Really Java.
Yeah.
You could Java interpreter.
Huh?
You could follow the Java source code and figure out.
Yeah, you could. Actually, might have been included in this that I had up. Yeah.
I didn't have to figure out what next is.
I was gonna say I don't know what that is. Oh, it's Python. It's generators. Yeah. So.
Man, that.
By the way, he didn't go to jail. They had him on trial, and they threw it out in '96.
We know it's boring.
Yeah, same.
So is that it?
That's it. That's all, folks.
We should.
Yeah.
Java's good more Python, you can do strings and stuff like that.
C++ could learn a thing or two. C++, they add stuff, but it always looks like they're useful things, but they always look so awful.
Yeah, well, it's always buried into something.
Yeah, and there's that. I mean,
Look up Well,